that you're using to predict the answer. And you'll never get some small set of rules that say what the network will do. But to answer the first question, this requires big data. That's how you get rid of linguists.
That's the lady over there.
Hi, Professor. Thanks for your presentation. And I would like to know, when you use the RNN, how do you choose between the LSTM and GRU?
I think that's a sort of fairly technical question that most of the audience may not be interested in, but these are two different kinds of recurrent net. They're really quite similar, and basically my approach would be you try and both and see which works best. They are actually, gated recurrent units are quite similar to LSTMs. So they're missing out the gating on the inputs, but I don't have a good answer. You just try and see which works best.
Okay, and my second question is, have you ever dealt with video classification?
With what kind of classification?
Video classification.
Sorry, I'm old and my hearing doesn't work well. Video, okay. Yes, I'm very interested in video because it looks like video is a very good source for unsupervised learning. But video is currently at the frontier. So if you look at our visual systems, we actually only process in detail something in the area of my thumbnail at arm's length. That's the only place we see fine detail. So I have this whole optic array, and I move my eyes around. So to first order, the way vision works is it's a sampling process. I have to decide where to sample next. And that's why magic tricks work. They get you to sample in the wrong places, and they can make you believe anything. So computer vision still isn't like that. Some robot vision is getting more like that. But basically in computer vision, they try and model all of the pixels and they have uniform resolution. We have very high resolution in a very small area, medium resolution, and then low resolution in a big area. And so the main feature of human vision is we do not process almost all the data at high resolution. If I were to make fine pixels with this whole optic array, almost all of those fine pixels I never process. One way to think about it is, suppose this was a whiteboard. And you take any old whiteboard that hasn't been erased quite properly, and you can see tiny little bits of structure. Some of you can see there's some little black fleck there. In a big optic array, it would take you months to process the whole optic array at the level of detail that I'm looking at when I see the little fleck there. And so the essence of human vision is not to process or to avoid processing things at high resolution. And we have billions of neurons to devote to it. These neural nets are much smaller, and they really ought to be doing this very sequential thing of only having a small area of high resolution, a bigger area of lower resolution, and deciding where to look next, and integrating it all. And that's going to be essential for video. In video, there's just too much data. If you take a single static image, and I give you a reasonable length of time, you can look in fine detail with the computer and everything. It's not the right way to do business, but you can do that. But you won't get away with that with video. And so I think video is going to be linked to visual attention and intelligent visual attention, intelligent ways of not processing most of the pixels.
Yes, last question here.
Like training any model, how do you avoid overfitting the neural network when you train it? So for example, if you feed the neural network with everyday photos of the Earth we take, it probably gets the idea that, oh, Earth is flat because all the pictures we take are flat, showing. But if it ever comes up with this concept that Earth is round, in other words, how do you make sure that the neural network has the ability to critically think? I guess we haven't got there yet, but I just want to know your thoughts.
Okay, I guess time's short. The best I can do is to say there are techniques for making neural networks much less prone to overfitting. And there's a technique I introduced called dropout, which randomly removes units. On each time you showed an image, you remove half the neurons. And it turns out that makes it work much better. And if you're interested in that, there's a video that I put on the web in 2012 called Brains, Sex and Machine Learning, or maybe Sex, Brains and Machine. Brains, Sex and Machine Learning. Part of the experiment was to see if you get more hits if you put sex in the title, and you do. But if you have a look at that video, that tells you one way of preventing this from overfitting. Okay.
All right, thanks very much. I have a few stories about Professor Hinton to share with you, because as I was preparing for this lecture, I was looking at Professor Hinton's family, and I realized he actually comes from a very interesting family with so many legendary people. For example, we use Boolean algebra every day in programming, and that was introduced by Professor Hinton's great-great-grandfather, George Boole. And the highest mountain in the world, Mount Everest, was named after another relative of Professor Hinton, George Everest. And Everest later became the middle name of Professor Hinton. And Hinton's family also has connections with China. So Joan Hinton, or better known as Han Chun in China, was a nuclear physicist. She worked for Enrico Fermi in the Manhattan Project. And she went to China in 1948 and spent a lot of time on dairy farms and made great contributions to the agriculture of China. So today we are with another legend from the family. So let's thank Professor Hinton again for... token of appreciation, we have a little gift for Professor Hinton. If you want to take a look. It's very Chinese. I know Professor Hinton likes carpentry, so a little...
Oh, that's very nice.
It's a Chinese knot, lotus, fish, and you have surplus every year. Fortune or luck. You want to see? Hold it, yeah. Okay, thank you so much. Okay, so I have a few people to thank for today's lecture. Of course, we thank Professor Hinton, and I would like